I'll start now then. Thank you. My name is Muthomi, as I've been introduced. I'm a master student specializing in structural engineering. The topic of my thesis was effect of carbon fiber reinforced polymer strengthening on the axial capacity and ductility of non-slender square concrete columns. I was ably assisted by Dr. S. Munyua and Dr. J. Muero of the University of Nairobi. My presentation will be as shown, and there will be a bar on your right just to guide you and keep track of where we are. To give you a little background, carbon fiber reinforced polymer strengthening is a composite material which relies on the carbon fiber to provide strength and stiffness, while the polymer provides a cohesive matrix to protect and hold the fibers together. CFRPs are used in aviation, shipping, automotive industries, bicycles, and civil engineering structures. In this study, CFRP was used in various configurations to strengthen concrete columns. In practice, concrete is composed of concrete that bears most of the compressive stresses and steel that bears most of the tensile stresses. Quality control measures are usually undertaken, and where material that's delivered does not meet the strength requirements, then the members are usually condemned for demolition. However, demolition is very expensive financially, time-wise, and to the environment. Alternative options to demolitions are the use of steel angles or the use of CFRP wrap. Some of the advantages of CFRP are its high strength, lightweight, corrosion resistance, ease of use, and speed of application, while its disadvantages are that it's easily damaged and it has poor response to fire. So, why would we need to retrofit? Probably because of design inadequacies or poor construction practices. In 2018, in an audit report of about 1,500 buildings, 44% of the buildings were found to be unsafe. So that's one reason we may need to retrofit. Also, because of the increasing rural to urban migration in all cities globally, we may need to increase the capacity of existing buildings in urban areas. It is against that background that the experimental study was conceptualized to find out how CFRP strengthens columns. From an academic standpoint, the problem was that most literature, all this implies change occurs mostly due to full confinement. However, some CFRP manufacturers claim that partial confinement offers same benefits with less material being used. There were 4 research objectives for this study based on concrete grade, reinforcement, degree of confinement, and the number of layers. 4 research questions guided the study, and 4 hypotheses were formulated. The significance of the study was that the knowledge gained will assist us to increase the load-bearing capacity of existing buildings, to reinforce buildings wrongly constructed, and to get a better understanding of using CFRP in the structural design process. One assumption made in the study was the use of prescribed ratios, even though there are slight differences because in the Indian standard, it's a step lower for the same target strength with what we have in Kenya. The scope of this study was limited to square columns and we only measured axial capacity and ductility, and for economic reasons, only 2 layers of CFRP was used. The study dug into literature and found out that CFRP strengthens columns by taking advantage of the Poisson's effect. This is where a column is subjected to uniaxial compression, it expands laterally. CFRP works by restricting the lateral expansion and therefore increasing the capacity of the column. Therefore, we looked at the 4 variables where concrete grade and reinforcement affect the lateral expansion, while the degree of confinement and the number of layers restrict that expansion. Other studies were done on concrete grade. As far as the author is concerned, there are no studies comparing plain and reinforced concrete, and no studies have been done comparing the degree of confinement. Other studies have been done comparing thicknesses. The conceptual framework of the study is Therefore, as shown, which guided our experiment, the experimental methodology, we had 3 concrete grades: plain, reinforced specimen, in a partial and full confinement 1 layer, partial and full confinement in 2 layers, and to improve the credibility of our results, 3 samples were made for each specimen. This was represented in a specimen matrix as shown, and these are presented graphically. A and B were the control specimens, while C to J had either 1 layer or 2 layers.
Good morning.
The specimen was manufactured.
Am I the one whose mic is not working? Sound hakuna?
Hello?
Yours, Dr. Dulo, we can hear ourselves. Maybe it's yours.
I'll continue. So therefore, the molds were made by marine ply, and oil engine oil was used as the shutter release agent. You can see elements with rebar and those without. Quality control measures were employed throughout the study. In this case, we had a reflow and quartering while we were batching the concrete. These are the specimens after curing. These are the specimens after, just before application of CFRP. This was the epoxy set and the 100-meter roll of CFRP. Carbon fiber was cut to size using ordinary pair of scissors and mixed according to manufacturer's specifications. This was the final specimens. Slight difference from what was conceptualized, but very similar. Testing was done in the setup shown. It involved 3 people. There was 1 person controlling the switchboard, which generally includes an electric outlet powering a concealed hydraulic actuator that pushed the specimen upwards, while a second person here read off the values of ductility, and the third person recorded the data. The data was then calculated and stress strain curves were plotted, which were basically in elastic and plastic phases. The axial capacity were represented in bar graphs. So in this case, C810 concrete, C1215, C1620, and the last 8 specimens, C to J, were compared with the control A and B. To find bar graphs where C to J are compared, and we found this was the trend. To make this clearer, the averages of this was made, and it was found that the weaker the concrete, the higher the effect of CFRP. In line with the second objective, compare the effect of CFRP of rebar on columns without CFRP. Trend was similar. Now we wanted to compare the effect of rebar on CFRP strengthening. To do that, this specimen was compared with this to get that. This specimen was compared with this to get the effect of CFRP on plain concrete. This specimen was compared with that to get the effect of CFRP on reinforced concrete, and for the combined effect, this was compared with this. We found, in terms of degree of confinement, we found that full confinement here was more effective than partial confinement. The same was repeated also for number of layers. 2 layers was more effective than 1. The same process was also repeated again for ductility of specimens. Ductility, the trends are discussed in the write-up here. And finally, these were the results. Similar comparison like that in ductility. It was interesting to note that when this specimen was compared to this, there was a decrease in ductility of about 4%. This was attributed to the rebar that made the column stiffer and therefore less ductile. Degree of confinement was also compared. Full confinement was more effective. Number of layers, 2 layers was more effective. And to find out the impact of the variables, it was represented in a radar chart. A radar chart is a graphical technique of visualizing multivariable data. In this case, we found concrete C810 had the highest effect, and the number of layers was closely followed. This is clearly illustrated by use of a tree map. Same procedure for ductility, found the number of layers. Two number of layers had the highest effect, using one layer had the least effect. The failure modes were then discussed of the various specimens before the findings were made. But the first hypothesis was accepted, the second failed to be accepted, the third and fourth were also accepted. The greatest takeaway of this research was the material efficiency, where double partial confinement was compared with single layer. In this case, we get a material saving of 14.3%, and the axial capacity increases for double partial, same as with the ductility. Some of the challenges the study experienced was that some equipment was not available, and the other human factors such as fatigue. In this case, you can see a skewed fiber in one of the specimens manufactured. To verify the experimental methodology, the stress strain curves were compared with formulas in literature, and they had high correlations. Random samples were manufactured and tested. The data was similar. The machines had been calibrated by Kenya Bureau of Standards in a year, and the failure modes were satisfactory, eliminating the existence of a probable fault in the machines. With the experimental procedure verified, the conclusions made here on concrete grade, reinforcement, degree of confinement, and the number of layers can thus said to be accurate. Recommendations were made from the study, and a design proposal was recommended in Appendix F. Recommendations for further studies were also made, and the references are here, given which follow the University of Nairobi School of Engineering guidelines, where no guidelines were provided in that. The study used the APA 7th edition, and an open source citation manager called Zotero was used. The appendices include the drawings of the fabrication and the instructions that were used to manufacture the specimen. Finally, have some calculations in the appendices and correspondence details before I conclude with an index of key of terms. I'd like to acknowledge CGP Consulting Engineers for providing the materials necessary to conduct this research. Thank you for your time. If you have any feedback, suggestions, and clarifications, I'll be happy to hear. Thank you.
Thank you very much, Adrian, for taking us through that very interesting presentation of your...
You're on mute. You're on mute, Doctor.
No, I'm not mute.
Oh, sorry. I can hear.
You can hear me?
Yes, I can hear. Sorry.
Okay. I was saying thank you very much, Adrian, for taking us through that very interesting presentation on your thesis. And
Yes.
now I would like to open the floor for any comments. And I hope someone is taking minutes. Is someone taking minutes? I know we are on record, being recorded, but is anyone taking minutes? Or you'll do it?
I'll do it. I'll replay the record, then I will take minutes. Yes.
Okay. Welcome everybody. Feel free. I know we had a chat, but it's not populated, so we are not too many. So I think we can afford to ask the questions verbally. Welcome, Dr. Muero, the co-supervisor. Maybe you have something to say, a remark before we open for everybody. Karibu.
Thank you. Sorry, I've joined late. I'm at home and I got delayed a bit, and the internet also is a bit weak. So my apologies for joining late. But I think I'll let others ask first. You know, I've read the document several times. Thank you.
Okay, thank you very much. Maybe I could kick off. I also have read the document several times, but I just wanted, Adrian, there are 4 points I wanted you to highlight, which I think are very important. One,
Yes.
you should include, I'm sure you have included, but you need to highlight a short section on theoretical framework. I know you have kicked it into the appendices, where you talk about the mechanisms of load transfer in a column. And also, you link this with the results of the interesting results you found about weak concrete being the most responsive to effects of the CFRC. And then you need to also highlight for the audience here why we went for a short column instead of a slender one. I'm sure even that is related to the mechanisms of load transfer. Then also, it would be interesting and important for you to give us the costs, effectiveness of this technology of retrofitting in terms of availability of the carbon fiber and the cost. I know the technology of retrofitting itself is not sophisticated, but what about the sourcing, the availability of the fiber itself? Those were my few points which I would have loved you to highlight, even as we proceed to other questions and answers. Thank you. If you can address those.
Okay, I'd like to start with the easier ones first. So the first one was, the most easiest was why short columns. Use the short columns. In this case, I'm using the Eurocode designation, so that's now called non-slender columns. So wanted the columns to fail by crashing and not buckling, so that you can see the effectiveness of the carbon fiber and how it affects the concrete itself. If it was a slender column, then buckling will increase more variables to investigate. I will have to find eccentricity, the percentage of eccentricity. So that was only done to make the study simpler and guided on the 4 variables that were investigated. Secondly was the cost effectiveness of the material. Carbon fiber reinforced polymer is fairly cost effective. It costs about 3,000 per meter squared to retrofit, and it doesn't require expensive material, only glue guns probably and grinders to smoothen the materials before application. So I'll say in total, including labor, I'll say probably 5,000 per meter squared to retrofit buildings. For the to link my results with CFRP, say with regards to concrete grade, I will say weaker concretes experience the highest effect because of they have the highest Poisson's ratio. So if you compress a column, it will naturally expand more, and that's how CFRP works. CFRP works by restricting the lateral expansion. So the weaker the concrete, the higher the effect. Stronger concretes are usually more brittle, and therefore there is less effect on them. And finally, to the theoretical framework, that's a slightly difficult question. Maybe I'll think about it, and I'll get an answer. We'll continue with the presentation.
Okay.
It's slightly challenging.
Sorry, just to, before we forget, when you're talking about a weaker yes. concrete, you yes. should also mention that chances of building or a column requiring retrofitting, chances of it having the weaker concrete than the stronger concrete are higher. Maybe that's the reason why they need retrofitting, just
Yes.
to make your work more practical.
Yes.
At this level, we are interested in also the practicability and applicability of your results. So it's always wise and good to add that aspect of the day-to-day, you know. For example, if somebody has had very strong concrete and maybe it failed, they may need to investigate why it failed. It may not have failed by crushing of concrete or weak concrete or wherever. So they may not find the carbon fiber the most appropriate method. Hence, the need to zoom into how much with concrete in this study. So you can add that. Thank you.
Doc, can I add something on that?
Yes.
Sorry, I get off and on, but on that thought, again, if I may add, I think if I understood properly, you know, the enhancement from this carbon fiber is dependent on how much the element deforms in the lateral direction, and as the concrete becomes stronger, the deformation in the lateral as you load in the vertical, it reduces a bit, and that could be one of the reasons why when you have stronger concrete, the enhancement is less, because as you load it, it doesn't bulge as much as the weaker concrete. Thank you.
Yeah, thank you. I think he has captured that. Yes, the floor. Let's engage Adrian as much as possible. Anyone? Maxwell. Maxwell, are you there? Maybe I can also ask something else.
Yes.
You have told us about the theoretical. Theoretical will be very important because you may want to compare your notes with some theory of sorts, isn't it? A model of the crushing mechanism, the load transfer mechanism. Then you try to relate it to your experimental results. That's why a theoretical framework is always very important, because that's an independent method of validating your result. Or otherwise, how did you validate your results? Because I know you can't just do an experiment and conclude just from it. What was your independent validator?
Okay, there are several other studies that have been done globally. So some used same kind of experimental investigation, and they confirmed their studies with finite element analysis and other numerical methods. So based on their conclusions, I compared them with mine, and I find that they were correlated, and therefore I also assumed mine was equally as correct.
Okay, thank you. So you need to bring out that very clearly. Otherwise, somebody will pin you down and say, you know, did you do the finite element? So bring that out very clearly, that the validator was borrowed from the literature, and you must package it very well, so that you remove yourself from any responsibility of somebody misunderstanding that that's your work. So that's very important.
Oh, thank you. I actually considered your comments on FEA, but it will take me considerable amount of time just to develop competency in that finite element analysis. Plus, I was also investigating more variables compared to other studies, so it will have taken much more time.
Don't worry, that is what you will do for your PhD proposal.
Okay, thank you.
Yeah.
Hello, Munyua.
Hello, Countdown. Thank you for coming.
How are you?
I'm fine, thank you.
You are basically working on the columns.
Yes.
Now, based on the reinforcement you are doing on the columns,
Yes.
let's take a situation whereby you have a multi-story building. How are you going to actually do the reinforcement? Because actually the loading varies from the lower floors to upper floors. Did you really consider that in terms of using the polymer for reinforcing your columns?
Okay, just to make to clarify on your question, whether I considered the different loads on different columns.
Yeah, because the lower floors will have heavy loads.
Yes, that's correct. So in the study, essentially, because carbon fiber is an expensive material, I'm saying you can use approximately 5,000 per meter squared to retrofit a building. So in the case, say you're retrofitting a whole building, at the bottom levels, you may need higher gains in strength. So you might have to use, say, 2 layers double confinement. But in the upper layers, where there is less load, you may use, say, partial confinement in 1 layer. So this study was just meant to improve our understanding and to fine-tune the parameters that is used in the structural design process by using CFRP.
Okay, well understood. Thank you.
Yeah.
It was a nice presentation.
Thank you.
Okay.
Something else, eh?
Yes.
Have you published?
As soon as I write the minutes of this, I'll now be in the final stages of sending my paper to a peer-reviewed journal. I'm looking at one called Structures. That is the journal of ISTRUCT, Institution of Structural Engineers in the UK. I have submitted a paper there before. It was rejected, but I got valuable comments from them. So I'm sure no matter the outcome there, I'll have something beneficial.
Thank you. Maybe you can also consider submitting an abstract to the IK conference that's coming in November. That will not be too rigorous for you, isn't it?
Not at all.
Just to help you refine
Yes.
and expose your work to a wider audience locally,
Okay.
without too much pressure from the journal. You say rejected your work once and you are still going up there. Okay.
No, I got valuable comments, so I don't mind at all. It was I was submitting so that for the sake of it, just to understand the publishing process.
Okay, so you know the route, you know the way to go about it, the formatting, the everything.
Yes.
For that journal, so it's much easier. Okay, thank you. Any other comments? I know we had booked ourselves between 10 and 10:30. We are doing very well. It's 10:27. Any other comments to help Adrian refine his thesis?
We have George Charlo from CGP Consulting Engineers.
Oh, okay. Maybe he can say something.
I don't know if he thought what I presented was accurate since we have already implemented on site.
Yes. I would like to congratulate you on the presentation. And we've been in the lab with you the last year, around the last 3 months of the year, working on it before we went to site. This is something I brought to you, and we wanted to do it with the university. so that we can try and know how we'll implement it on site. It's something new for us too, and it was something new for you and also the university. And we managed to engage the client, and the client agreed to buy all the materials. That's when we got the samples, and after getting the samples, we engaged Adrian, and luckily enough, he was also eager to learn on this carbon fiber and how we can help in retrofitting our columns on site. And we managed to do everything after getting all the results from Adrian. We managed to go on site and we implemented it. He also came on site and also did an inspection. And after that, we managed to finish the building. Now it's 6 floors up. And from when we got the contract itself, we had very weak columns with the classes of concrete as low as 15. And the design of the previous engineer was around class 25. And it was a very big process coming up with everything with the carbon fiber and how we decided not to do steel. And because we saw the carbon fiber was a very big, we saved a lot of cost. For the steel, we were coming to around 7 million for just retrofitting 2 floors of the building. That is 52 columns. And we came up with a cost of around 3 million by using the carbon fiber. That was the importation cost of everything from China, plus the clearance fees. So I'm very eager, and we wish to tell everyone in Kenya about the carbon fiber and this presentation we are going to do with the EBK. And I'm really eager and waiting for us to do that, Adrian. Thanks a lot for your presentation.
Thank you.
Thank you very much, George. I was also very keen and following up because also at the same time I was asked to supervise a building also here in Nairobi that needed retrofitting, and we recommended the carbon fiber, and it was done, and it was 4 floors. But again, we had a lot of issues with the costs were registering very low concrete. And when Adrian came with the idea, I was very eager because I was able to then do the academic and also the industry. And therefore, what I would suggest, because George, yourself, Adrian, Dr. Muero, we are here. The first place we need to present this is in the upcoming conference, because that's where the biggest audience of engineers, structural engineers, and even others and interested parties are. And I have witnessed, so I know from the lab, from the results, from the literature, even from the field, that this is something very promising. Considering also we can link it with condemned buildings. Most of the buildings condemned, especially if they relate to concrete columns, which I think most of them would be, without compromising this open spans, especially in basements and places like those. I think this would be a very interesting solution. So maybe after this presentation, we shall just unmute ourselves and open our videos and just see how we can go about it. But it's quite something very practical and very interesting. So any other input? So we have heard that this is partnership between academic and industry, and it is in reality it has been done, and we have done it parallel. So it's a very interesting project. And again, thank you very much, Adrian. I know our supervisor is not supposed to tell the student that he's doing well, because I'm not an examiner, I'm just a supervisor. But I must say, Adrian started this work, was it this year or late last year?
Late last year.
Late last year. And within within 6, 7 months, 8 months, he was able to have gone through the experiments, which most students find very difficult. Considering also we had a lot of challenges, we were communicating online with the COVID, we've not been able to even meet face to face, yet we are at a position we are actually preparing ourselves to submit for examination. So I would like to say this is quite encouraging, and I really would want to encourage you not to stop, to take advantage of the results and this collaboration with industry, and just, you know, take it to the next level after you are done with it. Thank you. I don't know whether Dr. Moro, you are still there. You can comment on what's your take on the way we have worked during COVID. We should actually change the topic to the COVID columns. COVID-19 columns. Because we worked just, you know, during the COVID. That's what we are busy doing. Dr. Mwero has dropped off. Anyway, I'm sure he would also support my sentiments.
There's a question from Charles Odira Maxwell. He says that we watched some engineers featured on one of the local TV stations using recycled plastics. Do you have any comments when you can compare the work and the carbon fiber? Not exactly, because in the case they are using material that is, they are using the manufacturing material to be used for construction. And in my case, I'm trying to save buildings already constructed. So maybe that's the slight difference.
Okay, yeah, thank you also for that observation of comparison. Have we exhausted the questions on the chat?
Yes.
We have?
Yes.
Okay. So if there is no other comment, Adrian, just proceed, do the minutes, share with me the minutes as soon as you can. Then we need to also engage, especially on the upcoming conference. The good thing is that I think it will be both online and physical, so you don't have to fear that you will not have the time.
Yes.
Yeah, and it also add value to your thesis.
Okay.
Yeah, thank you.
Thank you.
Thank you. Thank you, everybody.
Thank you, Dr.
For coming. Okay. George.